Greetings everyone. This is Yashwanth Nayaka, student of civil engineering, pursuing my degree from Sri Venkateshwara College of Engineering. I hereby presenting the seminar presentation on Tensegrity structure and their application to architecture under the guidance of Mr. Chaitanya K.M., Assistant Professor, Sri Venkateshwara College of Engineering. Introduction. Coming to introduction, structure are essential components of building, bridges, towers, and other construction that provide support and stability. In engineering, the architecture are several types of structure used to build various construction. One of the most common type of structure is beam structure, which is used to distribute weight and provide support. Beam structure are made up of straight pieces of material such as wood or a steel that are arranged horizontally to form a rigid framework. Another type of structure is an arc structure, which consists of a curved or an arch shape that supports weight and distributes stress evenly throughout the structure. Arc structure have been used for centuries to build bridges and other construction. A third type of structure is a truss structure, which consists of interconnected triangles and provides supports and stability. Truss structures are commonly used in bridges construction where they help to distribute weight evenly across the span of the bridge. A relevant newer type of structure is tensegrity structure. So what are tensegrity structures? Tensegrity structures, also known as tensionally integrity structures, are a type of architecture or a structural system that uses isolated components that are held in compression by a network of continuous tensional member. In other words, these structures are made up of series of rigid and flexible elements that work together to distribute force and maintain structural stability. The rigid elements such as truss or a bar are not in direct contact with one another, but are instead connected by a network of tensioned cable or a wire, creating a unique balance of a force that allows the structure to maintain its shape and stability. Tensegrity structure can be found in variety of application, from sculpture to bridges and even in a biological system such as shells and muscles. Now we know what is tensegrity structure. Let's study the history of tensegrity structure. A term tensegrity was coined by Buckminster Fuller, an American architect and inventor in 1950s. However, the principle behind tensegrity structure have been used for centuries in various forms such as suspension bridge and a cable stayed bridge. The earliest known use of tension and compression element in a structure dates back to the 15th century when Leonardo da Vinci designed a self-supporting bridge. In the 19th century, Robert Hooke and William Thomson, also known as Lord Kelvin, developed mathematical theory on a balance of a force in structure, paving the ways for the study of tensegrity principle. Buckminster Fuller, who is credited with popularizing the term tensegrity, began experimenting with the principle in 1940s and 1950s. He saw tensegrity as a way to create efficient and a lightweight structure, and his work had a significant impact on field of architecture, engineering, and design. Since then, tensegrity structure have been used in variety of application from architecture and engineering to art and a sculpture. Today, researchers continue to explore the possibilities of tensegrity structure with a new application being discovered in a field such as robotic, biology, and medicine. Because of the great scientists like Buckminster Fuller, Leonardo da Vinci, William, Robert, and many more, we are seeing new designs and technologies involving to the structure and the architecture. Now let's see importance of tensegrity structure in architecture. Tensegrity structure are becoming increasingly important in architecture due to their unique property and potential benefits. Here are some key reasons why. Efficient use of materials. Density structure are often lightweight and uses minimal amount of materials compared to other type of structure. This can result in cost saving and environmental benefits. Flexibility and adaptability. Tensegrity structure can be designed to be flexible and adaptable to different environmental conditions, making them ideal for use in wide range of application. Aesthetics. The unique appearance of tensegrity structure can add an artistic and aesthetic dimension to architectural design, making them visually striking and appealing. Resilience. Tensegrity structure have the ability to redistribute stresses and strain across their entire structure, making them more resilient to external force and impact. Structural integrity. Tensegrity structure are inherently stable and can maintain their shape and structure integrity even under extreme conditions such as earthquake or hurricanes. Now we know what is the importance of tensegrity structure in architecture. Before further, let's know about the compression and tensional element which are present in tensegrity structure. Compression and tension are two fundamental types of forces that are present in structural system. In the context of tensegrity structure, these forces are distributed across two types of elements, compression element and a tensional element. Compression elements are rigid structure components that are designed to withstand compressive force. Example of compression element in a tensegrity structure includes studs, columns, or beams. These elements are typically made up of materials such as steel, concrete, or a wood, which are strong in compression. Tension element, on the other hand, are flexible structure components that are designed to withstand tensile force. Example of tension element in a tensegrity structure includes cable, wire, or a rope. These elements are typically made up of materials such as steel, titanium, or a carbon fiber, which are strong in tension. In a tensegrity structure, the compression and tension element work together to maintain structural stability. The compression element resists the compressive force that act on them, while the tension elements distribute the tensile force throughout the structure, providing support and stability. The combination of compression and tension element in a tensegrity structure create a unique balance of force that allows the structure to be both strong and flexible. This allows tensegrity structure to be used in wide range of application from architecture and engineering to art and sculpture. So now we know how compression and tension member play important role in structures. Now let's study about geometric principle of tensegrity structure. Tensegrity structure are based on a set of geometric principles that govern the way components are arranged and connected. Here are some key geometric principles of tensegrity structure. Tensional integrity. The primary geometric principle of tensegrity structure in tensional integrity, which refers to continuous tensional force that hold the structure together. This tension is distributed throughout the structure, allowing it to maintain its shape and stability. Discrete compressions element. Tensegrity structure consists of discrete compression elements such as truss or a bar that are not in direct contact with one another. This allows for a great flexibility and adaptability in design of structure. Continuous tension element. Tensegrity structure also consists of continuous tension elements such as cable or a wire that connect the compression element, then tension element providing the structural stability support necessary for the structure to maintain its shape. Pre-stress. Tensegrity structure are typically designed with pre-stress, which refer to the initial application of tension in the structure before it is loaded with external force. This pre-stress helps to ensure that the structure remains stable and maintains its shape under the varying load and condition. Synergy of force. Tensegrity structure are characterized by a synergy of force in which the tension and compression force work together to create a stable and efficient structure. This allows for a greater strength and durability, as well as more efficient use of materials. Non-linear response. Tensegrity structure have non-linear response to loads. This means that their deformation is not proportional to the load applied. Energy efficiency. Tensegrity structure are highly energy efficient as they use only the minimum amount of material necessary to maintain their stability. Self-organized. Tensegrity structure are self-organized, meaning that they can adapt to changing load and condition without external input. Organization. Tensegrity structure have a hierarchical organization which smaller units combining to form larger structure. This allows for complex multi-level structure to be building using the same basic principle. Overall, these geometric principles allow tensegrity structure to be both strong and flexible while also being lightweight and efficient in their use of materials. These principles have inspired a wide range of application in fields such as architecture, engineering, and art and biology. Now let's see some example of tensegrity structure in nature and architecture. Biological cell. Cell in a human body such as muscle cell uses a tensegrity structure to maintain their shape and function. The cytoskeleton of a cell is made up of a rigid protein and a flexible filament that work together to create a stable and flexible structure. Tree trunks. The trunks of many trees also use a tensegrity structure to support their weight and withstand external force. The trunk is made up of rigid wood, fiber, and flexible bark that work together to distribute the force of wind and gravity. So this is a biological cell. We can see the outermost layer act as a tension and the inner act as a compression. Here are some example intermediate filaments which are acting as a compression member and filaments are acting as a tension member. This is a Buckminster Fuller's geodesic dome, one of the most famous example of a tensegrity structure in architecture. Is a geodic dome designed by Buckminster Fuller. This dome is made up of a series of compression truss and a tension cable that work together to create a strong and lightweight structure. The Eiffel Tower. The Eiffel Tower is also an example of tensegrity structure with compression elements such as iron, lactic work, and tension elements such as cables that holds the structure together. Cable-stayed bridge. Many modern cable-stayed bridge also use a tensegrity structure with compression elements such as pylon and tension elements such as cables that supports the bridge deck. Sculptures. Tensegrity structure are often used in sculptures such as work of Kenneth Snilson and Thomas Sarceno who create intricate and delicate structure that rely on balance of tension and compression to maintain their shape. Now let's see some advantages of tensegrity structure. Lightweight. Tensegrity structure are typically much lighter than traditional structure of a same size and strength as they use minimal amount of material to achieve their structure stability. This makes them easier to transport, assemble and disassemble. High strength to weight ratio. Tensegrity structure have a high strength to weight ratio meaning they are able to support large load with minimal material use. This makes them ideal for application where weight is critical factor such as aerospace and robotics. Flexibility. Tensegrity structures are highly flexible and can adapt to change in their environment such as wind and seismic force. This allows them to withstand external forces and remain stable under varying load and condition. Easy to assemble and disassemble. Tensegrity structure can be assembled and disassembled quickly and easily as they consist of discrete compression element and continuous tension element that can be easily connected and disconnected. Minimal environment impact. Tensegrity structure require minimal excavation and uses minimal amount of material which makes them environmental friendly and sustainable. Aesthetically pleasing. Tensegrity structure are often used for their unique and aesthetically pleasing design as they offer a wide range of possibility from form and shapes. Coming to application of tensegrity structure in architecture. Bridges. Tensegrity structure are used in cable-stayed bridges where they support the bridge deck and distribute the load of a bridge. Example includes the Leonard P. Zakim's Bunker Hill Memorial Bridge in Boston. Roofs and domes. Tensegrity structure can be used to create lightweight and flexible roofs and domes such as Eden Project in UK and Geospheres in Germany. Space structure. Density structure are used in space structure such as inflatable lunar habit and the Mars rover due to their lightweight and adaptable nature. Art installation. Density structure are used to create unique and intricate art installations such as the work of Kenneth Snelson and Thomas Scarron. Towers and sculptures. Tensegrity structures can be used to create tall and slender towers and sculptures such as Tower of Wind in Yokohama, Japan, and Solar Fountain in Santa Fe, New Mexico. Stadiums. Tensegrity structures have been proposed for a stadium roof such as the Al Bayt Stadium in Qatar due to their stability, ability to span larger distance and support heavy loads. These are some overview of architectural project that uses tensegrity structure. The Denver International Airport tent. This tensile structure spans over 900 feet and is supported by tensegrity framework. The Kuwait Pavilion at Expo 2015. This pavilion features a tensegrity structure made up of a series of cable and steel rods that creates lightweight and flexible forms. The Eden Project Biomes. These large bubble-like structures are made up of a series of geodized dome and tensegrity framework that create a stable and lightweight enclosure. The 2010 Shanghai Expo theme pavilion. This pavilion features a complex tensegrity structure made up of series of intersecting steel cables and compression struts that creates a unique and dynamic form. The Singapore Sports Hub. This sports stadium features a retractable roof supported by a tensegrity framework, which allows it to span over 300 meters without the need of any additional support. Let's see some case studies of tensegrity structure in architecture. The Georgia Dome, Atlanta, US. The Georgia Dome was an indoor stadium with a seating capacity of 71,000. The roof of a stadium was supported by a tensegrity structure made up of a series of steel cable and compression truss. The structure allowed the roof to span a distance of 317 meters without any additional support, making it one of the largest span tensegrity structure in the world. The Eden Project, Cornwall, UK. The Eden Project is a botanical garden with a series of diodized dome and a tensegrity framework that create a stable and a lightweight enclosure. The dome are made up of hexagonal and a pentagonal cells which are connected by a tensional cable and compression truss. The largest dome has a diameter of 110 meter and a height of 50 meter. The Al Bayt Stadium, Qatar. The Al Bayt Stadium is a football stadium with a retractable roof supported by a tensegrity framework. The roof is made up of a series of steel cable and compression truss that allows it to span a distance over 400 meters. The roof can be opened or closed in just 20 minutes, allowing the stadium to adapt to a changing weather condition. The Solar Fountain, Santa Fe, USA. The solar fountain is a kinetic sculpture made up of a series of tensegrity structure. The sculpture features a large ball and that appear to float in the air, supported by a network of a steel, cable, and compression truss. The ball is covered with a solar panel which power the fountain and lights. The Tom Barley International Terminal, LAX, USA. The Tom Barley International Terminal at Los Angeles International Airport features a dramatic tensile roof supported by a series of tensional cable and compression stress. The roof covers an area of 1.3 hectare and has a height of 16 meter. The roof allows natural light to filter into the terminal, creating a bright and a airy space. There are three types of tensegrity structure. One is truss-based tensegrity structure, cable-based tensegrity structure, hybrid tensegrity structure. Now let's see about truss-based tensegrity structure. Truss-based tensegrity structure are a type of tensegrity structure that uses trusses as the compression element and tensional cable or a wire as a tensional element. In truss-based tensegrity structure, the compression member are connected by joints or nodes, which are held in a place by a tensional member. The tensional member are pre-stressed to provide stability and strength to the structure. These creates a self-supporting system that can resist external load and maintain its shape. Truss-based tensegrity structure are highly versatile and can be designed in a variety of shapes and sizes to suit different applications. They are often used in architecture, engineering, and art, where their lightweight and efficient design make them an attractive option. One of the key advantages of a truss-based tensegrity structure is their ability to span a long distance without a need of any intermediate supports. This makes them ideal for use in bridges, roofs, and other structures where large open space are required. Overall, truss-based tensegrity structure offer a unique combination of strength, stability, and flexibility, making them a popular choice for a wide range of application. These are some examples of truss-based tensegrity structure in architecture. Stuttgart Airport Terminal Roof, which was constructed in 2004 by German engineer Leonhard and Andra und Partner. Eden Project Biomes, which was constructed in 2001 in UK by British architect Nicholas Denvert Art Museum. The Frederick C. Hamilton Building was constructed in 2006 and designed by American architect Daniel Libeskind. Olympic Stadium München. The stadium was constructed in 1972 and designed by German architect Ferry Otter. Water Cube Beijing. The water cube was constructed in 2008 and designed by Chinese architects. So these examples demonstrate the versatility of a stress-based density structure in architecture, as they can be used to create a variety of shapes and forms that are both functional and aesthetically pleasing. Coming to cable-based tensegrity structure. Cable-based tensegrity structure are complex system of tension and compression elements that are held in stable configuration through the balance of interface force, internal force. The term tensegrity is construction of tensional integrity, which refers to the ability of a structure to maintain its shape and stability through the interaction of tension and compression element. In cable-based tensegrity structure, cable or a rope are used to create tension and hold the structure together, while rigid elements such as truss are used to create compression and provide the overall shape of a structure. The cable are arranged in a partner of interconnected triangle or another geometric shape that create a stable self-supporting structure that can withstand external loads and forces. Cable-based tensegrity structure have number of advantages over traditional structure, including their ability to span large distance without the need of intermediate support. Their lightweight and efficient use of materials and their ability to absorb and distribute loads in a flexible and dynamic manner. These properties makes them ideal for variety of application including bridges, roofs, and other long-span structure, as well as artistic installation and sculpture. These are some examples of cable-based tensegrity structure in architecture. Denver Art Museum, Frederick C. Hamilton Building, Punit de la Major in Biomes, Argentina, Olympic Stadium in Montreal, Canada, George Pomdion Center in Paris, France, Eden Project in Cornwall, United Kingdom. Coming to hybrid tensegrity structure are combined of two or more type of tensegrity structure such as cable-based and truss-based structure, or a combination of tensegrity structure with other structural system like beams or arch. These structures offer several benefits such as increased stability, greater load-bearing capacity, and the ability to achieve more complex geometrics. Hybrid tensegrity structure can be used in variety of applications including bridges, buildings, and even spacecraft. The design and analysis of hybrid tensegrity structure can be complex as they require thorough understanding of the behavior of each type of structure used and their interaction. Finite element analysis and computational modeling techniques are often used to optimize the design of hybrid tensegrity structure and ensure their structure integrity. Overall, hybrid tensegrity structure represents an innovative approach to structural design that combines the benefits of differential structure system to achieve optimal performance and aesthetics. Here are some examples of hybrid tensegrity structure in architecture. The Almelo Bridge in Seville, Spain, which was constructed in 1992, designed by Santiago. The Mercedes-Benz Stadium in Atlanta, US, which was constructed in 2017, designed by HOK and Buro. The Yokohama International Passenger Terminal in Yokohama, Japan, constructed in 2002. The Beijing International Stadium, also known as Bird's Nest, constructed in 2008, designed by Herzog and De Moran. The Vidyasagar Setu in Kolkata, India, constructed in 1992, designed by Sachin Bergman Partner, and a bridge is a hybrid tensegrity structure that combines a cable stayed system with a truss-based tensegrity structure. Now let's see the comparison between types of tensegrity structure. Truss-based tensegrity structure. Strength. Truss-based structure offer high compressive strength and stiffness, making them ideal for applications such as bridges and buildings that require significant weight-bearing capacity. They are also relatively simple to construct and analyze. Weakness. Truss-based structure may not be flexible as cable-based structure, making them less suitable for application. Where flexible is a key requirement, they also tend to be less visual appealing than other type of tensegrity structure. Cable-based tensegrity structure. Strength. Cable-based structure offer high flexibility and tensile strength, making them ideal for applications such as suspension bridge and other structure that requires significant strength or span. They are also visually striking and can be used to create complex geometrics. Weakness. Cable-based structure may not offer as much stiffness or compressive strength as truss-based structure, making them less suitable for some application. They can also be more difficult to construct and analyze due to complex nature of tension force. Hybrid tensegrity structure. Strength. Hybrid tensegrity structure can be offered the benefit of both truss-based and cable-based structures such as high strength, stiffness, flexibility, and load-bearing capacity. They can also achieve more complex geometrics than either type of structure alone. Weakness. Hybrid tensegrity structure can be more difficult and complex to design and analyze due to combination of different structure. They can also be more expensive to construct than single type of structure. These are some few factors which should be considered while selecting a density structure for architectural project. We should consider the purpose or function of a density structure. We should see aesthetics, the aesthetic quality of a structure, including the desired shape, visual impact, and material choice. Site condition. The site condition include the topography, soil condition, wind, seismic activity must be taken into account when selecting a tensegrity structure. Budget. The budget available for a project will impact the type of tensegrity structure can be chosen, as some structure may be more expensive to construct than others. Maintenance and durability. The maintenance requirement and expected lifespan of a structure must also be considered when selecting a tensegrity structure, as some structure may require more upkeep and have a shorter lifespan than others. Environmental impact. The environmental impact of a structure, including the material used and energy consumption, should also be taken into account. Local regulation. The local regulation and building codes must be followed when selecting a tensegrity structure, as some structure may not be permitted in certain areas or may require additional permits and approvals. Challenges which are faced in the design and construction of tensegrity structure. The complexity. Tensegrity structure are highly complex and require advanced design technique and engineering skills to create a stable and structural sound system. Non-linear behavior. Tensegrity structure exhibit non-linear behavior, which means the small changes in one part of a structure can have a significant impact on an entire system. Material selection. The selection of a material for tensegrity structure is critical to their success. The material used must be strong enough to support the intended load and must also be able to withstand the environmental condition in which the structure will be placed. Construction challenge. The construction of a tensegrity structure can be challenging as complex geometry of the system may require specialized techniques and equipment to assemble. The use of cable and other tension element also require careful attention to detail to ensure that the system is properly tensioned and balanced. Maintenance. Tensegrity structure may require more maintenance than traditional structure. Due to the complexity of our system, the material used, this includes regular inspection to ensure that the tension element remain properly tensioned and there are no sign of corrosion or damage. Now let's see some potential benefits and a future direction of tensegrity structure. The potential benefits of integrating a tensegrity structure into a suitable architecture requires material efficiency, energy efficiency, flexibility, and aesthetics. Tensegrity structure uses minimal materials to achieve a high level of tensegrity structural integrity, making them an attractive option for suitable architecture. Tensegrity structure are lightweight and have a low surface area to the volume ratio, making them more energy efficient than traditional structure. Tensegrity structure are highly flexible and adaptable, allowing them to be easily configured or expanded as needed. And tensegrity structure offer unique and visual striking design, making them a popular choice of architects and designers. So future direction for research and development in tensegrity structure includes developing a new material and a fabrication technique to improve the strength and durability of a tensegrity structure. Exploring new application for tensegrity structure in an area such as disaster relief, transportation, and a space exploration. Tensegrity, the dynamic behavior of tensegrity structure under different loading conditions, which will improve the understanding of their performance and allow for more accurate design and analysis. Developing a new computational tools and simulation techniques to improve the design and optimize of tensegrity structure. Coming to the conclusion of this topic, the implementation of tensegrity structure has both challenging and potential benefits. The challenging includes the complexity of the design and construction as well as the lack of established design codes and standards. However, the potential benefits of a tensegrity structure includes their material and energy efficiency, flexibility, and unique aesthetics, which make them attractive for a suitable architects. Continued research and development in a tensegrity structure, including the development of a new material and a fabrication techniques, and the investigation of the dynamic behavior under the different loading condition will help to further improve their performance and visibility for a range of application. In conclusion, while there are challenges in the implementation of tensegrity structure, their potential benefits makes them an exciting area for research and development in architecture and engineering. So here are some recommendations for architectures and designers interested in using tensegrity structure. The research and learn about tensegrity structure. It is essential to understand the principle and the mechanism behind a tensegrity structure as well as their advantages and limitations. Work with experienced engineer and fabricators. Tensegrity structure are complex and it is crucial to work with an experienced engineer and fabrication who has expertise in designing constructing the structure. Consider the site and context. Tensegrity structure have unique aesthetics and it is important to consider the site and the context in which the structure will be located to ensure it fits within the surrounding environment. Incorporate suitable design principles. Density structure have potential benefits for suitable design such as energy and material efficiency. Architects and designers should consider incorporation these principles into their design to maximize the benefits of using density structure. Test and analyze the structure. Density structure can be challenging to analyze and predict their behavior, especially under different loading conditions. Therefore, it is crucial to test and analyze the structure thoroughly and ensure it is safety and stability. Stay up to date with the research and development. Density structure are an area of an active research and development with an ongoing advance in materials, fabrication techniques, and design methods. Architects and the designers should stay up to date with the latest research to advantage, incorporate these advancement into the design and projects. And here are some reference of a project done by some authors. First, the tensity structure from Stability and Symmetry by Robert E. Skelton. Tensity-based architecture design for sustainability by Alj Akashmedja. A tensity system in architecture and overview by Ashwini Kumar Sharma, Gaurav Singh Kushwan, and Satish Kumar. Stuttgart Airport Terminal Roof by Ingova Architects, Eden Project Biomes by Germanshaw Architects, Frederick C. Hamilton Building at the Denver Art Museum, Olympic Stadium Mansion, Watercube Beijing by PTW Architects. Thank you. Thanks for listening. If you like this video and the topic, please do like and share.